found a really cool article about like people who believe in paranormal things, and they're like, I think they're just like, they're actually like paranormal beliefs. So like people who think they like kind of yeah. And it's only like I don't mind this one. I like it a little cool.
I was like, so much confusion. Speaking of brain, I'm gonna like miss one meeting and forget. Yeah, I do. Like one today, one tomorrow, one Friday. Yeah. I'm free tomorrow. I like spilled tea on my jacket this morning. Does that count?
Yes. I have to get
Oh, yeah. Well, first I almost forgot.
No, I like it.
Oh, can't do that.
Hi, Claire.
What kind of tea?
I was 7 and my aunt was like, I haven't purchased like a fine like kind of orders and just like sends me all this stuff like that. So like right now it's like and then sweat like same thing. Yeah, it's pretty good. It's just really black. Yeah, it's okay. Specialty teas from like a those treat from my mom's birthday every year, and I have some of that like I like actually use to like get all that. Green tea, but it doesn't experience that.
Hey, Seth. Okay, we've got 12:30, so why don't we get started? Good afternoon, S&P. Good afternoon. Happy Wednesday. I meant to say something on Monday. I had just on Monday finished grading the assignments that you turned in last Wednesday. You might remember that last Wednesday we were in a U and we had a terrific conversation. And so all of that writing that you had done was graded and returned to you on Monday. And I think that was a job well done on your part. Thank you for your thoughtful considerations about Sally French's situation. And we do try to link all the details that we're learning about physiology and the facts of light and so forth to socially relevant issues. And I think people did that very well in their conversation and also in their writing. So congratulations. And I think probably the remaining 3 writing assignments, you will not have to bring in your written report. We did that as a backup this time because this is the first time that I've been using Blackboard to have you submit your assignments, but I think that worked sufficiently well that I'm willing to get rid of the training wheels and go all the way to electronic. So thank you all for your good work on that. We've got some great news. Friday's an exam. Can we give it up for the exam? Yeah? People are psyched up, right? All right, now you're all pros at this. We've done this once before. And at the risk of beating a dead horse, I will go to this one final time. You've seen this, okay? Right? It's all about the format, the content, and what's going to be on there. TED-Ed is our friend. Thank you again for the feedback on TED-Ed. That was really helpful the other day. I found that to be enormously instructive. People seem to like it. They wanted a few more hours, so we're going to extend, or we'll add a grace period, we'll put it that way. So still think about it as due at 9 o'clock so that you have a little alert in your brain. but there won't be any penalty for the 3 hours thereafter. Okay, so that was helpful feedback on TED Ed. Oh, by the way, I don't think I mentioned this to my stats class this morning. This is the first time I've been using TED Ed, which you all knew. I just found out that fortunately I'll be able to present a poster on this in Florida at the end of this academic year. We go to NITOP, a lot of the folks here in our department. NITOP is the National Institute for the Teaching of Psychology. And we meet with other psychology professors from around the world, and we talk about the things that we're doing in our classroom and so forth. So I'll have something to say at that point about TED Ed. I don't know what I'll be saying because the data are still coming in on TED Ed, and our experience with it isn't finished. But I think relatively few people across the world are probably using TED Ed, so you're truly on the cutting edge. Thank you for that. Look forward to sharing at the conference, really, your experiences with TED Ed. Okay, here's how to practice. This is available out on the S drive. You've seen this a few times before. Not a lot of points associated with this. It's only 40 points, so a small fraction of the overall grade. But it does help us consolidate our thinking and make the transfer into long-term memory from all these things that you're learning in class and through these different exercises, writing assignments, and TED Ed questions. All right, so we have a very busy schedule today. We have a lot to do because we want to finish off our conversation on color perception, and then we want to make our way through form perception. We only have the one PowerPoint on form perception, but it's a fairly long one, and I want to give it its due. But what I do like about color is it's so easy to do color demos. We've had fun with color demos already where we had the color after effects and simultaneous color contrast. We've had some good opportunities to work with that. I wanted to play around with PowerPoint's color wheel. How many people have used PowerPoint's color wheel before in other classes? Maybe for creating assignments, you use PowerPoint's color wheel. I find it to be enormously instructive for understanding color science. So I'm going to click really anywhere in here. You do this all the time. You probably change the color of ink from time to time when you're creating Word documents or Excel documents or PowerPoint documents. So if you click on really anything, I'm going to go to that small letter A where I could change the color of print. And I'm going to go down here and click on More Colors. Okay? Because we don't have enough computers in this room, I won't ask you to do this on the exam, but I hope that you'll have the chance to play around with this. I'm going to go to the sub-menu that's called Custom, and you might see here that I have the red, green, and blue guns that we talked about last time. So what's coming out of there are these 3 guns. And really, for any given pixel, if you will, it's almost being bombarded by 3 different wavelengths of light. Okay? And what's cool about this is PowerPoint and Excel and Word give you complete control over the intensity of those. Okay? Now, just to give you a feel for the range, you can scale up any one of these guns on a scale that goes from 0 to 255. Just a little bit of techie information here that you wouldn't need to know. That's called 8-bit resolution. Has anybody ever heard of 8-bit or 32-bit resolution? Maybe when you're listening to stereo equipment or you're buying stereo equipment, they'll say this is recorded in 16-bit resolution or 32-bit resolution. The idea there is it basically tells you how many steps you have from the lowest to the highest value. And here we have 8-bit resolution, and a bit is a binary digit, so it's either a 0 or a 1 in computer world, right? Things are either on or they're off, 0s or 1s, and we have 8 such bits, and they can assume 2, because it's on or off, to the 8th power, different possibilities. 2 to the 8th turns out to be 256. Okay, so we have 256 steps that we could use, and the way the PowerPoint refers to that is 0 to 255 gets us to 256 possible steps. Who's following that? Okay? So we basically have 256 possible values that we can assign to our blue gun momentarily put to 0. Okay? So I'm going to hop over here. Can people all see red, green, and blue in the back? Is that fairly, Claudio, is that clear to you? Okay. Let me play around with these numbers. I'm going to hard code them. I'm going to turn this one all the way down. I'm going to turn this one all the way down. And over here, you can see I get my new color, and here's the current color. I must have clicked in on some of my yellow. I have a lot of yellow lettering in my titles. I think I clicked on one of my title letters that gave me the current color, but now I've got this going on here. I can jack the red all the way up to 255. Okay, there it is. I can turn that one down. Okay. I can jack the green all the way up to 255. Okay. Turn this back to a simple 0. And I can jack the blue all the way up to a 255. Who's following that? So far, so good. Okay, all right. Can you tell me how to make this yellow? This shirt is getting very old and tattered, so I apologize for the bad cups, but it makes the point. This shirt is about 590 nanometers. Okay? It's a yellow shirt. There is no yellow gun. We're getting a pretty good yellow, not quite the same yellow as that, but we're getting a pretty good yellow there. How do I get my yellow going here? I'll start you on. Oh, Meg's got something. Red and green. Okay, let me turn the black all the way down. Meg, do you want to float me a couple of values on the scale that goes from 0?
250 green.
Okay.
245 red.
Okay, 250 green, 249. Wow. Can you see that turned yellow there? Okay. And we did this with our filters the other day. We had the red and blue filters, and we saw that there really is no yellow. Like this thing is yellow there. But psychologically, you're getting a really, I hope you're getting a really good yellow here. Okay. Most people with normal trichromatic vision would be getting a yellow there. Okay. All right. All right. How am I going to make white? I don't have a white gun. Yeah. Change the blue to 250? All right. All right, people okay with all of that? Yeah? All right. So the other fun thing that I'd like to do is we talked about, I think Claudio reminded us the other day that brown is extra spectral, that it doesn't appear on the spectrum. How are we going to get a really good Hershey bar color here? Can anybody help us out? I want to get a really nice looking Hershey bar color. So we want a brown, a chocolatey brown. Okay? We don't have a chocolatey brown as one of our 3 options. Okay? How are we going to do that? Okay? Low levels of red and green. So, and what do you want me to do with blue? Okay, blue's out. Low levels. Do you want to float me a number, Claire? Our scale is 0 to 255-ish. So
Like 100.
100. And also for green, 100. We're getting there. I think that's a pretty good brown, right? I mean, we might make it. It's dark chocolate. Okay. Okay, right? And it's kind of fun is you can sort of hang on one of these and just inch it up and see if that makes it better or worse. I think that's going the wrong way. I think I need a little less green and maybe a little more red. I don't know. Oh, you get the point. We're in the neighborhood there, right? We could play around with that and make that a little bit tighter. Okay, so really cool. And you can get all these different colors just with these 3. Okay? All right. Right. Let's also now learn a little bit about how to describe these different colors using the PSYC system. I wonder if anybody can tell us about the PSYC system without my projecting it here. The PSYC system is a system for describing color in any stimulus. We have 3 PSYC coordinates. Anybody remember that from the video? Okay, thanks, Claire.
It's hue, intensity, and brightness.
Well, okay, there are 3 different dimensions of color. Hue, yep, okay. Hue, saturation, and brightness, right? Hue, saturation, and brightness are 3 different dimensions. We have these PSYC coordinates. And this might come up on the test. And what happens here is we have 3 coordinates that essentially describe your red gun, your blue gun, and your green gun. Okay, so they go in this sequence, R, G, and here's B. And I'm going to put B like that because the rule was that when we give some decimal value to R, G, and B, the set of them, the 3 of them, have to add up to 1 in the RGB system. Okay? So what we can do is we can say, well, here's a pretty good white light, and I think it was Zach who told us a moment ago that the white that you see over here would be created by keeping relatively equal intensities in all 3 of the guns, right? We turned all of them up to 250 or something like that, okay? So what we would then say is that they're all equal. This one would be, if you will, a 0.33. This one would be a 0.33. What would this one be? If they all have to add up to 1? 0.33, okay? So we actually don't have to specify that one. We typically leave this one unspecified, and we report these 2 because you can always infer the last one as being what's ever left over to get you to 1. Okay? Who's following that? Does that work? Okay. So for example, if it were the case that I had a light that was 0.8 and the light over here was 0.1, what would the B have to be? 0.1, okay, because the whole thing has to add to 1. So given that the rule about the CIE descriptions of lights, okay, physical descriptions of light, has to always add up to 1, we only need to specify these two, and the rule is always give R first, give G second. Okay, that's always the rule. Okay? So let you play RGB with me here. We'll go over to, and that's the full spelling, which I will never test you on. Commission Internationale de la Éclairage is CIE, is what that all stands for. You don't need to jot that down, but that's where it comes from. This was an organization, an international commission, located in France at the time, that tried to get some kind of standard for describing colors using this system. Okay? So that's our RGB system. Okay, wow. That didn't come out so well with the lights up. Okay, what color are people seeing? Okay, can you float me the RGB coordinates for that stimulus, approximately? 1, 0 is all we need to say, right? They only need to have 2, okay? So you're giving me 1, 0. Okay, let's go on to a different stimulus. By the way, I wish you could see this screen. This screen is a magnificent red, but you're getting hit with a lot of white light here also because we haven't turned those shades down, okay? So why don't you yell out the CIE coordinates for this one? 0, 1, okay. How about CIE for this one? 0, 0, right, okay? So all of the weight, so to speak, is landing on that unrepresented coordinate, okay? How about this one? That's kind of interesting. 0.5, 0.5, okay? And nothing left over for the blue gun, right? Nothing left over for the blue gun. That's supposed to be white. 0.33 and 0.33 as an approximation, okay? Okay, and then we were making our Hershey bar, okay? Just for fun, I wonder if we can see how well we're actually doing here. Can we get somebody who will be our camera person, and we'll turn on my photometer, and we'll see if we can get this thing going. What you do is you point your photometer at the screen, you hold down the trigger, and in just a moment or two, some coordinates pop up, and they tell you how many photons as expressed in candelas per square meter, but they also give you over on the side what the reading is in CIE coordinates. Okay? Anybody want to play our camera person and make these measurements? We'll see if our guesses are well corroborated by this. You have somebody who will do that for us? Okay, thanks. Thank you, Ken. Yeah, I think that works. So, all right, there's that. And why don't we, so we have an idea, the rest of us have an idea. You can sit if you're more comfortable, that's fine. Why don't we go back and we'll just take a moment on this. This is the one that everybody thought was red, okay? And we'll let you hold down you can hold down the trigger, right? And just keep it down because it does take a while at this low light level. It might take 3 or 4 or 5 seconds until you get a little pop there. Okay, does it tell you how many candelas you're getting?
It says 10.6.
10.6, okay. Hang on, all right, and here I come. This might be real bright, and you can let go of the trigger, if you will. Here comes the next stimulus, okay? Why don't we shoot that one?
43.7.
Okay, so the first one had 10 candelas per square meter, and this one is 40-something. Okay, so not only are they differing in wavelength, but they're also differing in total illumination. Why don't we do another one? I think that's going to be way low. And usually the lower it is, the longer it takes the photometer to respond. 9, okay, so that's way down there. Hang on, this one's going to be bright. 50.9, okay, so you get the idea, right? As it's getting brighter, the total number of candelas per square meter is going up, okay? Now, why don't we try this? On this, can you do that one again? We'll shoot that one again. And once you get the number, okay, can you now flip over to the side panel here, and can you read these for us? So there's the CIE coordinates are on the side.
It's 51.4. Oh, wait, it changed when you did.
Okay, that's all right. You might want to let go of your, so get a reading, and then you can let go of the trigger.
Okay, so 47.
Okay.
0.4 and 0.5.
Okay, 0.4 and 0.5 is what she recorded. Okay, now what we would have said a moment ago was, I think we called this 0.5 and 0.5. So there's a little bit of blue squeaking in here that shouldn't be in here, probably coming from that. Okay, because we've turned when I made this slide, I cranked blue all the way down, red and green all the way up. So it came out 0.4, 0.5-ish, right? Okay, can we do one more? Right? We do This, hopefully, we're going to be roughly at 0.3, 0.3 for your second two coordinates on your side.
Yeah, 0.3.
Okay, and 0.3 and change. Okay, so you can see that's corroborated by the CIE coordinates in our photometer. Okay, thank you, Gabby. Thanks very much. Really appreciate your doing that. Okay, so, oh, and by the way, for those of you who are in the research class, if you are doing anything with color or you just want to take a quick measure on how much light is coming off of your screen and you want to put that in your measurement system, in your methods section, when you're describing your measurements, that's fine. Okay, so enough about all of that. I think we've made our way through the color demos. All right. We also had a follow-up talking about trichromatic vision. Lots going on here. And we talked about this bit in our video. Why don't we do it this way in the interest of time? Why don't we see, well, maybe somebody can tell us how to interpret this. This is a monochromatic system, right? And we said that this is vulnerable to all kinds of errors, right? Vulnerable to all kinds of errors. If you're monochromatic, you can see you're sensitive to light, right? But there's all kinds of errors that can arise from a monochromatic system. Can anybody begin to describe how the monochromatic system is vulnerable to errors? Okay, thanks.
So because it absorbs more light at if the stimulus is twice as bright in point A, than it is at point B, then the two will perceive the same.
Okay, really good. All right, so and this is a slide that through the years some people have stumbled on. Some students find this one a little bit challenging. Zach just nailed it. Okay, so the idea is, if you'll bear with me, I'm going to say that at wavelength A, remember the wavelengths are going from 400 to 700 nanometers. We've done that many, many times. Okay. At wavelength A, right about here, I don't know, maybe that's 500-ish or so, we'll call it wavelength A. It's this particular mechanism is going to be absorbing about, let's say, 25 units of light, right? Okay? And at B, we're going to be absorbing about twice that amount, okay? Right? So this will respond the same way to A and B if A is twice as bright as B, right? If we throw out twice as many photons there, and we're catching only 25% of those, that's going to give us the same amount of absorption overall as would be the case if we have a typical light here, but we're absorbing twice as much. So the idea is you can trade intensity of light for the wavelength of light, and this animal can't tell you that that's different. Right? You can have we know that intensity is one feature. We know that wavelength is another feature. Those are different physical features, but this animal, under appropriate conditions, could not distinguish those. They couldn't tell whether we had changed the wavelength of light or whether we had increased the light level like that. Okay? This mechanism would be firing the same way. And that's, I think, a subtle point. So I'm happy to say more about that if folks are not entirely clear. Yeah?
I guess the wavelength is different, or it's the same.
Okay, so at one point in time, we're going to stimulate them with something down this side, okay? A wavelength of light that might be from our PowerPoint color wheel, something toward the bluish end of the spectrum. I've got my blue gun going up pretty high, okay? At some other point, I'm going to turn on a different stimulus, and now maybe I've got something more like my green gun going, okay? Right? And you and I can easily tell blue from green under most conditions, okay? Right? But what's happening here is that this particular photopigment will be absorbing more photons here because the arrow is higher and it's landing higher on the y-axis than it would over here. Okay? So all other things equal, it would absorb more of these longer wave photons than that. Okay? Does that work for you? Yeah, okay. But then what we can do is we can say, well, why don't we, since we're only getting 25% of these photons, why don't we just go ahead and double the intensity of the light? We'll make it twice as strong. So we'll crank up the intensity of the light while still presenting that bluish light, but now we'll make it a brighter blue. And now all of a sudden, this mechanism will absorb the same number of photons with that brighter blue light than it would with this dimmer green light. Okay? So bright and dim is one dimension of variation. A different dimension of variation is blue versus green. Okay? But this thing gets fooled, right? Because it's going to have a univariate response. It's either absorbing a photon or it isn't. Okay. All right. All right. Something similar goes on a few slides later. We talk about this two-pigment system, which is kind of interesting. Okay? Just to walk us through that, what I think we mentioned in the video is this, that if we have broadband light, like what's coming through the window right now is broadband light. Okay, so we get all different wavelengths of light. We're going to get, if I were to draw the schematic of the light that's coming in, we're getting some down here at 400, some here at 700, and everything in between. It would be this big, big rectangle. Right, would be the wavelengths that are coming in to this system, right, this big rectangle. And we're going to get these mechanisms, mechanism 1, mechanism 2, absorbing lots of light because their peak sensitivities are getting hit, their secondary sensitivities are getting hit, and so forth. So they're both absorbing a whole lot. And when you have broadband light, these two are firing similarly, and we experience whiteness. Okay? Who's okay with that? Is that working for us? No? They're experiencing whiteness. And that's good, because we have broadband light, and most of us would like to think of that as being white light. Here's what's really cool. There is this balance point, right, this midpoint that we see here. We call this the neutral point. Instead of having this really broad band light, I can have a single light right about here. Okay? It's going to hit right in between the two, and mechanism 1 and mechanism 2 are going to be equally sensitive to that well-selected light right there. That one light is a laser. It's just, and what would it be? Like maybe 570 nanometers. It's going to be a little bit on the green side of yellow, kind of a yellowish green. Put up just a yellowish green, just like that. Okay? This guy would absorb some amount of light, and this guy would absorb the same amount of light, which is exactly what's happening when we have the full band. These two are in the same firing ratio, or the same absorption ratio. So what's really cool about that is we can fool this animal into thinking that the animal is looking at white light if we have a very well-selected laser right here, okay? Right, because we're going to generate the same kind of biological response, same ratio of biological responses. This, again, is very similar to the diagrams that we drew the other day when we were talking about the color after effect. Who remembers that we had a red mechanism and we had a green mechanism, and we stared at those geometric shapes for a while, and we adapted one of them down, right, okay? Well, same kind of a thing. We're always looking at the ratio of those two mechanisms, and here we're looking at the ratio one more time. For the broadband light, the ratio is 1 to 1. For this well-selected light, the ratio is 1 to 1. For here, for this particular wavelength, A is a little bit to the left of dead center, so now mechanism 1 is firing more than is mechanism 2. So this will now have a bit of a skew, where this guy's firing more, so it's going to look like a shorter wavelength light rather than a longer wavelength. Pretty cool. Okay? And then, of course, you can trick us. Maybe I can find it one last time. I think I have it. Well, we've already seen how when we put up R, G, and B, all we have is 3 spikes for us, right? We don't have the full spectrum. We have just 3 spikes, but that's enough to fool our system into thinking that we're white. We're seeing a white stimulus. Right over here, we have RGB. There isn't broadband light there, but you're fooled into thinking that you've got broadband light because all 3 of your cones are firing simultaneously and in equal proportion. Who's okay with that? All right. All right. Any additional questions on trichromatic vision? Yes, please.
So in dichromatic vision, would, like, if you had 2 like guns that were...
That would do true. Yeah. Oh, thank you. That's a fantastic question. Let me tell you just how messed up the dichromatic system is, because Alexa is right on it. Okay. So, oops, that's the wrong day. I want this one. Yeah, there's a whole family of metamers. So the most extreme case is here's the big broadband and here's just the one. If I understand Alexa's question, you're saying suppose I had 2 right here. Would that do the trick? Yeah, that would do the trick. And then we can also go like this. Let's go equal interval just out a little bit. That's going to do the trick. Oh. Right? Okay. That's going to do the trick. So there's a whole family of dyads, right? That would make this guy and that guy fire at the same level. And every time that happens, the animal sees white. Right. The more pigments that you have in your retina, the harder it is to fool that system into seeing white, but you can get there eventually. Something else on trichromatic vision. Okay, why don't we go over to form perception? Okay? Love this topic. Absolutely love form perception. I think it's so cool that Fourier has done what he's done here. Okay? So, by the way, we had an acronym in form perception, and maybe you can tell us what our acronym was. I think I hear. FAPO, okay? FAPO is what we learned about in this one, okay? That's our acronym. The F in FAPO stands for? The A in FAPO stands for? Okay, the P in FAPO stands for? Okay, and the O stands for? Orientation, okay? Right. In our stats class, we were working with phase, amplitude, and frequency earlier today in a different context. But let's go to that now. I'll open this up. And sometimes a picture will say 1,000 words for us. So this is a difference that we're seeing here in spatial frequency. This one is twice that, okay? I wonder if I can get there really quickly. So this might make the whole concept of spatial frequency just a little bit more tangible. I'm going to try to find an online piano keyboard. Now, how many people have ever heard these songs, Somewhere Over the Rainbow? Okay. See if we can get the first two notes of Somewhere Over the Rainbow. Who's with me? All right. If those were visual stimuli, they would look like this. Right? Lower frequency, higher frequency. Right? Okay. And that's actually a frequency doubling. Okay. So the number of compressions and rarefactions on your ear when we played those two notes was twice as high for the second note as it was for the first note. In the visual space, this cycle is occurring 2 times per unit space here and 4 times per unit space here. We call that an octave, but the idea is that is the spatial frequency difference. They are the same in all other properties. That was the F in FAPO. Here is the lower amplitude, higher amplitude, right? Okay. Who can remind us about the Michelson contrast formula here? That was one of our TED Ed questions. The Michelson contrast formula. Connie's got it? Yeah?
So basically just find like the highest from the lowest.
Okay. Yeah, right. So the Michelson contrast is all about taking a particular stimulus and finding the highest and lowest luminance levels, L max, L min. We find that difference, that goes up top in our numerator. We find that sum, it goes into our denominator, and this would be lower contrast than this. This is a little less peaky, so to speak. That is to say that this light is not quite as light as that one is, that dark is not quite as dark as that one is. There's not as much luminance contrast. Okay? The peaks and the valleys are not so far apart from each other here as they are here. Okay? Oh, by the way, for a lot of the cells in your primary visual cortex, let's say we have a cell in primary visual cortex that is tuned to this spatial frequency and also tuned to vertical orientations. It likes vertical orientations. Typically, as you crank up the contrast, the cell will fire more and more action potentials. And then as you back off the contrast, it tends to fire fewer action potentials. So it's basically saying, it's basically reporting to the rest of the brain, how much evidence do I have for high contrast at this particular spatial frequency? And it gives you many or fewer action potentials in a way that's driven largely by the total amount of contrast. Okay? So these two are differing from phase. Okay? This is the one that tends to throw students off a bit. Right? The next one is trivial. We all understand orientation, vertical and horizontal, but this one sometimes throws folks. If we think about starting at the low end of this light cycle, on our scale from 0 to 255, what would this bar be? Okay, and this would be 255, right? Okay, so we're starting 0, then 255. Same values, but now in the opposite order, 255 then 0. Okay, right? So we're starting on the light side rather than starting on the dark side here. Okay? Here I've made them 180 degrees apart, but I could have made it fractionally different, right? I could have brought this a quarter of the way through or a third of the way through. Right? Okay, and orientation is the one that's really, really obvious. Okay, questions on FAPO? That sets the stage for a lot of stuff. Yes, please.
So the white is like the higher end of the wavelength?
It wouldn't be a higher wavelength, it would be higher intensity.
Okay.
Okay, right. That's okay. That's a higher intensity, right? So if Gabby were up here one more time and we had Gabby place that device right here or right here, she'd get a really low value here, and this number would pop right up. There'd be a lot of photons driving that thing, and we'd get a really high luminance value, probably on the order of 200 or so. Okay. Okay. All right, then we get into some of this stuff. This is kind of interesting. We started out with some simple square wave profiles, and I think you can see why this is called a square wave. It does look square-ish, right? But we can contrast that with a stimulus that doesn't vary abruptly as you go from left to right. It varies smoothly as you go from left to right, and you might get something like a sine wave. Still, here's a dark area, corresponds to that dark area. Here's light. So same spatial frequency, same starting phase. It starts out on the light side, and it ends just with a splash of light over there. But this is now smoothly varying, that's abruptly varying. And if we were to draw the corresponding profiles, we'd have something that looks now more like this for that smoothly varying one, rather than that step function, that square wave function. Who's following that? Okay. What may or may not come through in the video, I can never be sure what video quality you might be looking at, is we can have luminance here where we're going up toward white, down toward black, up toward white, down toward black. This middle line is a pretty middle gray, as you might imagine. Okay? That's because this is luminance, high numbers of photons, low numbers of photons. Right? I can change this axis and make that, instead of luminance, we can make it wavelength, such that as we go across space, we're putting out light that is relatively long wave, 700 nanometers, or shorter wave, okay? And we might be going from what I'll call red to green, and halfway between red and green is going to be our yellow, right? And I don't know how well that came out on the video, but that's a pretty neat looking slide, I think. Just you have a sinusoidal modulation in frequency as you're going from left to right here. Right? It's pretty cool. Pretty cool. Okay. So then we get into this whole idea about trying to convert this, okay, where we have now how much luminance do we have across space, into the frequency domain. This was the genius of Fourier. He's trying to get us to think in terms of frequencies as opposed to space. And he's showing us here frequency, and he's giving us a lambda. What did the lambda stand for? Length, okay? And so what we could say is, how long is this wave peak to peak? And the answer is from here to here, it's that long. Okay? And you can see that we get a bright white section and a bright white section there that's about that long. We have a much smaller frequency right over here. I'm sorry, a much smaller wavelength, I should say, peak to peak. That is just that big. Okay? So that's going to be a smaller wavelength. It's also going to be a higher frequency. Okay? So wavelength and frequency are inversely related. How many people follow that? This inverse relationship between wavelength and frequency. So sometimes you'll see wavelength, as you see here, and then sometimes they'll be describing things by putting 1 over wavelength. 1 over lambda would be frequency. Okay? So they could have just given you an F for frequency. Okay? They could have called this the frequency. Here's an F for frequency, or 1 over lambda. 1 over lambda. Okay? Can somebody tell me about why this thing is positioned where it is, and why it's as tall as it is? And why this thing is positioned where it is, and why it's as tall as it is. Any notion about that? Okay, Abby's got some.
Is it A has a higher amplitude?
Good, okay.
Frequency, and B has a lower amplitude, longer.
Right, perfect, thank you. And a little confusingly, the word contrast here is used synonymously with amplitude, but Abby picked that up correctly, okay? So we have a amplitude over here that's not quite as steep, peak to trough. We're not quite as high as we are over here. Okay, so we're trying to represent that on this graph by saying that we have less energy, less contrast here than we do here in the frequency domain, the 1 over lambda domain. Okay? It's pretty cool that our nervous system, as we'll find out, is actually doing these frequency analyses all the time. As you're hearing my voice, your cochlea is performing a frequency analysis on my voice. Whenever you've heard anything in your life, your cochlea has always been performing a frequency analysis in the auditory stimulus. And as you're looking out, and it turns out that Zach has a highly striped shirt there that's a fairly high spatial frequency. Okay, we have neurons in our visual cortex that are tuned to different kinds of spatial frequencies. Okay, so unbeknownst to Fourier, by the way, he was able to figure out that maybe you can take any complex pattern, an auditory pattern, a visual pattern, a stock market pattern. There was no stock market at his time, but there were people that I worked with in my lab that left neuroscience to go work on Wall Street so they could do Fourier decompositions of stock patterns and pull out all of the sine waves that are inside of all that, which is pretty cool, right? He was trying to build a better cannon for his buddy Napoleon, and he was looking at how you use sine waves to describe how heat moves through different kinds of metals. The cannons are made out of metals. It's cold in Russia in the winter. Your cannon still has to fire in Russia. He's trying to figure out things about heat transference. He's decomposing everything into these sine waves, and he's beginning to express things in terms of 1 over lambda. Okay? At the time, he didn't know that while he was looking at all that stuff, his brain was actually performing a Fourier analysis. He didn't know that his ears were performing a Fourier analysis, but he's the one who planted the seed that, 150 years later, neuroscientists and psychologists began to figure out this is actually how our brain is making sense of the world. Okay? So there he is. There's our guy. Okay. Somebody want to give us the gist of this slide? This was something that we spent quite a bit of time on in the video. If it helps, you might look at that and you might look at the top one just to remind you of how this whole slide comes together. What's a simple take-home message from this slide? No? Maybe we're not entirely sure. Or maybe it's really obvious, I'm not sure. But here's our final product on the slide. This is what we're building to. And this looks like a simple square wave. The genius of Fourier is that inside of this square wave, there is hidden, if you will, all these different sine wave patterns. Okay? It's actually in there, or at least we can decompose this final image into all of its constituent sine waves. The same thing is true, by the way, of my voice. It's going to turn out that you can take my voice and decompose it into all of these pure tones. So let me just play for you a pure tone. Pure tone generator. And we did this one before. We played 440. Okay. There's probably some energy at 440 hertz, or the corresponding wavelength, in my own voice, right? And there are cells in your cochlea that are picking that up, just like there are cells in your brain that are looking at this, but are responding to that component of that. So that thing is actually in there, believe it or not. You wouldn't know it just by looking at it, and this is why I think Fourier was so clever, to come to the intuition that this can be broken down into all kinds of sine wave components is pretty powerful. Pretty powerful. So those rudimentary sine waves added together will get that and that will add to this, okay? And then that and that will add to this, and we can keep on going until eventually we get to this, adding these higher and higher spatial frequencies. What I do want to call to your attention is something that I think Abby's pointed out for us already. So there's the picture that we're looking at to start with, that splash of light, dark, light, dark. There's the profile across space, X in A, and then over here in the tilted A, you get the representation in the frequency domain, where you get that one spike. Okay? Then we add to that a higher frequency stimulus that has less energy, but is further this way. Okay? And when we add that spike and that spike, we get these two spikes. And that looks like that picture. Right? Okay? And if you put that on top of that and add them point by point, you get almost like a Mexican hat that is starting to approximate this. Then we add more of these little guys out here, and we get closer and closer and closer until we finally get to that product. Who's following that? Is that working for us? Yeah. Pretty clever that our brain is doing all of that. Okay. Then we can introduce some phase shifts. We can just move the relative position of some of these, and we wind up with a similar pattern, but not exactly the same pattern. We might be able to get to a triangle wave just by manipulating the phase of the underlying component. So we always have FAPO to play with. We can manipulate the frequency, the amplitude, the phase, or the orientation. And when we do that, we wind up with different products out here. Okay. So there that is, just contrasting the square wave with the triangle wave, and the only difference between those is a little downstroke right over here. Right? So that's one starting position, and now we're starting on an upstroke right over here. So just a slight change in phase in these components is enough to change the overall bit. So phase matters. Right? If we manipulate the phase of our stimulus, we wind up with very different kinds of images. Okay. Here's our friend from the 1940s. This is Groucho Marx. Okay? And we can filter Groucho Marx in a way that's a little bit similar to the filters that we had the other day with color. We had a red and a blue, okay, and we had long wave pass and we had short wave pass. Who remembers that? Does that sound okay? You can have different kinds of filters that will allow low spatial frequencies to pass through. And if you did look at this image and only saw low spatial frequencies, it would look like that. Okay? That might be something very roughly akin conceptually to your red filter. It allows long wavelengths of light. This is allowing low spatial frequencies to pass through. Okay? Then we can look through a different lens and see that only very high spatial frequencies pass through. But again, the genius of Fourier is this and this are actually embedded in here. Okay? And we have neurons that are picking up and responding to this. We have a different set of neurons that are responding to that. And their ensemble is giving us the perception of this. Pretty cool. Same thing here. I think this is I think that's the skyline of Memphis, Tennessee. If anybody, I've not been to Memphis, so if somebody can tell us if that's true or not. But one of the authors of this book is from Memphis, and I think he took that photograph, then decomposed this into low, medium, and high spatial frequencies, and reassembled them over there. Right, so all these different ways of computing that. Okay, so how does our nervous system begin to do this? We have these different receptive fields. Here we have a receptive field with an on center, and here we have 3 of them. Here we have, if you will, dark, light, dark, and we have that same pattern over here, but happening over a smaller region of space. So this is going to be tuned to relatively high spatial frequencies, like on Zach's shirt, okay? And this is going to be tuned to much lower spatial frequencies, kind of like what we're getting here. The bottom half of this is really quite dark. The top half of this is quite a bit lighter than the bottom half is overall, okay? So you could have sort of on and off right over here, okay? Over a relatively large region of space picked up by this. Okay, questions so far? There's a lot of new ideas in there and a lot of counterintuitive ideas. We'll pause for a moment and see what questions people might have. So if we now take those receptive fields that we had and we try to play our Goldilocks game here, right? So we have one particular receptive field and we might get a relatively poor match here because we have an on center. So far that's good, but a lot of light is falling in the surround. Over here, we're getting both light and dark in the center and light and dark in the surround. Over here, we're getting a pretty good match. The center is stimulated largely with light, and there's predominantly darkness in the surround. So this cell is going to fire more to this stimulus than it will to this stimulus than to that or to that, right? Because the size of the receptive field is lining up very well with how the luminance is distributed in these cases. Who's following that? Is that working for us? Okay. All right. And what's really cool, I think, or a really nice idea, is that if you look at how your cortex is organized, if we were to take an electrode and begin pushing it through your cortex, we can find that we have a certain orderliness along the orientation dimension. That's the O in FAPO, right? So some cells are going to be tuned to horizontals, others to verticals, others to 45 clockwise from vertical and so forth. And it's really quite orderly. And if you go along a different dimension, in your brain, you'll find that the cells are tuned to different spatial frequencies. Okay? So again, unbeknownst to Fourier, he had no idea that his brain was doing all this, but his visual cortex was performing an analysis that we now call the Fourier analysis in his honor. So pretty neat that our brain is actually organized in such a way as to do a Fourier analysis. Okay. Why don't we go on to some other ideas? I really wanted to get to the contrast sensitivity function. Okay, and we have just a few minutes to talk through this idea. Okay, kind of interesting. And we can put up different spatial frequencies, really, really fat bars to really, really narrow bars, and we can ask at what point they become invisible to you. And for certain of these, we're very sensitive. We need very, very low levels of contrast in order to see them. For others, we would need much, much higher levels of contrast in order to see them. And the contrast sensitivity function is something that we can measure for you. It's something that we can measure for you across your lifespan. We can measure it under different lighting conditions. Photopic would be full sunlight. Here we are at dusk. Here we are at scotopic vision when only your rods are operating. Okay? So at some point, we might be able to see, I can tell that Zach is over there, but I can't actually tell that he's got a striped shirt on, right? Because the frequencies on his shirt are going to be over here, And we can fairly easily see that under this nicely illuminated condition. But if we turn down the light levels overall and only our rods are operating, they operate over a much narrower range of spatial frequencies, and particularly toward the lower end of the range. So we're not going to be able to, we can still see that he's there, but we'll lose some of these finer details that we have in the higher spatial frequencies. Right? Love this one. This is kind of fun. Just, different animals that you might know and what range of frequencies can they see. Right? Pretty cool. Okay. Here's the infant versus the adult. And this, maybe we'll end on this one. I think this is a real trophy for psychology. I think psychologists got this one right. Who remembers talking about the preferential looking paradigm in Intro to Psych? Maybe if you've done anything in a developmental class, you know that you can figure out what the baby might know about the universe by preferential looking. You put up two stimuli, and the baby will respond to the novel stimulus. Okay? So what you can do is put up a purely gray screen, or you can put up a really, really low spatial frequency stimulus on one side and see if the baby can pick up that the low spatial frequency stimulus is over here. I think you vary that randomly trial over trial, and you see what the baby can follow. And then what we can do is try to reconstruct the contrast sensitivity function. So this is the picture that we're really interested in. But the baby at 5 months can't see the really high spatial frequencies in this, but can get a lot of the frequencies and would probably be presented with this and experience this. Okay? So this is what this picture would look like to that baby at 5 months. Okay? A little bit earlier in its life, it wouldn't even have those moderately high frequencies. It would have more low-end frequencies, and it would now look like this. At 1 month, things are really quite blurry. Right? So the sensitivity to these higher frequencies come on board over the first 8-9 months of visual experience. And so this is what the world may have looked like to you when you were at these various ages. On the condition that we're working only in the luminance domain here. Clearly you had color as well, but that's how blurry things were. Okay, so that's our introduction to the contrast sensitivity function. Okay. Gets us most of the way through all of this. We do have a couple of minutes, and so I'll just open it up for questions and see if anybody has anything on form perception that they wanted to go over. Sorry about the bright lights. Okay, Claire's got something.
Just to be clear on back to the Trichromatic Vision with the one pigment system.
Okay. Yeah, you might think of it as a cone, right? You might think of it as a photopigment that's either going to catch the light or not catch the light. Okay. Something else. Isabel's got something, please. That's okay. That's all right.
Back to what Claire was talking about on the Trichromatic Vision.
Yeah.
How does the red light work? Chromatic vision work? How is A or B twice as much as B or 50%?
Okay. So back on this slide. Yeah. Okay. All right. Okay. I can present to you a blue light. I can present to you a green light. So far, so good? Okay. I can present to you a dim blue light or a intense blue light. I can present to you a dim green or an intense green. Okay. So we have two variables that we can change there: the frequency, okay, blue versus green, and the intensity of those lights. Okay. So what we can do is we can play a trick on our monochromatic friend over here, and we can say that we're going to change the light from green to blue, and we'll get differential responding because they're more sensitive here than they are here. Right? But we can also say that we're going to crank up the intensity of this light, okay? And now they're still going to get 25% of that light, but it's one thing to get 25% of $1. It's another thing to get 25% of $2. Okay, right? So we're cranking up the light from $1 to $2, okay? Does that work for you? Yeah, all right. Okay, and we're just about there. Thanks for a great session. Look forward to seeing you on Friday. All right? And I'll see some of you in about 10 minutes.